Hello everyone, welcome back to my channel. This would be the third video on Physics Chapter 3 Current Electricity, and in this video I'm going to talk about the current density and Ohm's law. Okay, now we know that current has a direction and it flows opposite to the direction of flow of electrons. The direction of the current is always opposite to that of the direction of the flow of electrons. Let's see. Suppose this is a conductor, and some potential is applied across the two ends of the conductor. Okay, suppose a potential is applied across the two ends of the conductor. Then the electrons of the conductor, they will move, they will drift towards the positive end of the conductor. That we have studied in the topic drift velocity in the first video of this chapter. Then the current flows in the opposite direction. The current flows in the opposite direction to that of the electrons. Okay, that is a sign convention. If electrons flows in this direction, current flows in the other direction. Okay, so the direction of the current is opposite to the direction of the flow of electrons. So current has a direction, but it is not a vector quantity. Okay, current has a, we used to think that like any quantity which has a direction is a vector, okay, but that is not true. For a quantity to be a vector, it must satisfy or it should obey the vector law of addition. Now let's see, current has a direction, but why is it not a vector quantity? Let's see. Suppose a current of 3 ampere flows in this direction and a current of 2 ampere flows in this direction. The current of 3 ampere, the current of 2 ampere makes 90 degrees with each other. Then the resultant current will be 3 plus 2, 5 amperes. Current, they always add up. Current always adds up like a scalar quantity. It does not depend upon the angle. Alright? So the resultant current will be 3 ampere plus 2 ampere, which is equal to 5 ampere. So the current simply adds up like a scalar quantity and they do not depend upon the angle. Is it okay? That means they do not follow the law of vector addition. According to the law of vector addition, okay, the resultant will be given by suppose this is one vector A, and this is another vector B, and the angle between the two vectors is theta. Then the resultant of these two vectors will be given by a square plus b square plus 2ab cos theta. Okay, a square plus b square plus 2ab cos theta. So this is how two vectors are added. But here for the current, okay, when two current adds up, they do not depend upon the angle. So, but they adds up like the scalar quantity. They adds up like a scalar quantity, not like a vector quantity. If current is a vector quantity, then it should satisfy the vector law of addition. Whereas for the current, okay, they do not obey the vector law of addition and they just adds up like a scalar quantity. So vector we can call it, currents we can call it as a scalar quantity. Are you getting that? Are you clear with this? Okay. We know that current has a direction and its direction is always opposite to the direction of the flow of electrons. But having direction doesn't mean that it is always a vector, okay? Now, if any quantity has to be a vector, it should satisfy or it should obey the law of vector addition. Whereas for a current, okay, if two current meets, they add up like a scalar quantity. They do not obey the law of vector addition. Hence, current is not a vector but a scalar quantity. Alright? Suppose there is one current coming in this direction, 5 ampere. There is another current coming in this direction, 3 ampere. The angle between them is 60 degrees. Then these two current adds up, okay, and it will give you 5 plus 3, 8 ampere. See? So when two currents meet, making some angle in between them, okay, they will just add up like a scalar quantity. Here, the resultant current will be 5 ampere plus 3 ampere is 8 ampere. So current adds up like a scalar quantity. They do not depend upon the angle, and hence they do not obey the law of vector addition. Hence current is a scalar quantity. So we need a vector which will play the role of the current. Okay, we need a quantity. Since current is a scalar quantity, not a vector, so we need a certain quantity, which will be a vector, okay, which will be a vector and will also obey and will also play the role of the current. Since current is a scalar quantity, so we need a quantity which will play the role of the current but is also a vector. That is known as your current density. Current density denoted by vector J. This current quantity, this current density, vector J, okay, is going to play the role of the current, and it is also a vector. So this quantity is required here because this quantity, okay, is a vector and it is going to play the role of the electric current. Now, current density is given by the formula current upon the area. Okay, current upon the area, and the direction of this current density, okay, is same to that of the direction of the current. The direction of this current density, okay, is same to that of the current. Now, and here A is your area. In order to understand this, I'm going to consider a conductor. Suppose this is a conductor in which a current flows in this direction. Okay, the current is flowing through the conductor in this direction. Now let me consider a small cross section of this conductor. Okay, I'm considering a small cross section of the conductor of area A. Then the current density will be given by ratio of the current to this area of cross section. Note that this area should always be perpendicular to the current. Okay, the area of cross section, the area that you have considered, should always be perpendicular to the current. Now, in some questions, if you find that, okay, suppose this is your current is flowing in this direction, okay, I is in this direction. Suppose this area A is given to be like this. Your area A is given to be like this, is given in this form. Your area is given in this form. This is your area A. Then you have to take here we see that your area A is not perpendicular to the current, right? This area A is not perpendicular to the current. It may be making some angle 30 degree, 45 degree with the current. It's not perpendicular. So you need to consider the component of A which will be perpendicular to the current. In that case, the formula for current density will be I upon here. Your area A, cross-sectional area A, is not perpendicular to the current, so we can resolve this area A into two components. Suppose this area A, it makes an angle theta with this line, okay? Suppose your area A makes an angle theta with this line. Then the component of A along this angle theta will be A cos theta, and the component of A perpendicular to A cos theta will be A sin theta. That is how we can resolve, okay, A into two components. Here the area A is not perpendicular to your current, so we have to take the component of A which is perpendicular to the current. So your area A, suppose it makes an angle theta with this line. Then the component of A along this angle theta will be A cos theta, and the component of A perpendicular to A cos theta will be A sin theta. So A has been resolved into two components, A cos theta and A sin theta. Now, which of these components is perpendicular to your current? A cos theta. So in that case, your current density will be given by I upon A cos theta, correct? In that case, your I will be equal to vector J into A cos theta, alright? So this implies I is equal to J dot A, because scalar product of any two vectors, dot product of any two vectors is given by AB cos theta. So JA cos theta will be given by J dot A. Are you clear with that? Is it okay? Where I is the current, A is the area, okay, current density is given by I upon A, where I is the current, and A is the area perpendicular to the direction of the current, okay? A should always be perpendicular. The area that you have considered should always be perpendicular to the flow of current, okay? So, the direction of this current density J, just remember that the direction of this current density vector J will be in the same direction to that of the current, okay? Here I represents the current that is flowing, and A is the area, and the area should always be perpendicular to the flow of the current. So this is known as your current density. Now the next topic will be the Ohm's law. Ohm's law. Okay, Ohm's law. Ohm's law states that all physical conditions remaining constant. Physical conditions means the temperature, the pressure, the humidity, okay, etc. So all physical conditions remaining constant, then the potential difference that is applied across the two ends of the conductor will be directly proportional to the current flowing through it, okay? That means more the difference in the potential, more will be the current that is flowing through the conductor. Less the potential that you set up, less the current will flow through the conductor. So Ohm's law states that all physical conditions remaining constant, okay, physical conditions means we can say temperature is kept constant, pressure is kept constant, humidity is kept constant, okay, etc. So all physical conditions remaining constant, then the current flowing through the conductor, is directly proportional to the potential difference applied across the conductor. Okay, is directly proportional to the potential difference across the ends of the conductor. So all physical conditions remaining constant, the current flowing through the conductor is directly proportional to the potential difference across the two ends of the conductor. That means the potential difference applied across the two ends of the conductor is directly proportional to the current. If we convert this proportionality constant to equals, we have a constant, okay, some constant into I. So that constant will be known as the resistance of the conductor, okay? Here, only if R is constant, only if the resistance is constant, then V will be proportional to I. But see, it doesn't mean that R is always constant. No, resistance is a variable quantity, okay? Resistance is a variable quantity. Resistance can be increased, resistance can be decreased. Is it okay? But for the Ohm's law, resistance should always be constant. For if resistance is not constant, then V will not be proportional to I. Alright? So for an ohmic conductor means those conductors which obey Ohm's law, the resistance should always be constant. So resistance is constant only for an ohmic conductor. That is, those conductors which obeys only Ohm's law. Or else, okay, in other cases, in general, resistance is not always constant. And if resistance is not constant, then this Ohm's law is not applicable. Only if the resistance is constant, then the Ohm's law is applicable. So R is constant only for an ohmic conductor, that is, those conductors which obeys Ohm's law. Now let us try to prove the Ohm's law. In order to prove the Ohm's law, we need to recall the first video that I have uploaded for this chapter 3 current electricity, where we discussed about the drift velocity through the classical story of electric current. We have discussed about drift velocity, and also we have discussed about the relationship between electric current and drift velocity. So let us try to recall that relation. The drift velocity is given by the relation minus E means charge of the electron, times the electric field, okay, that is applied across the conductor, into tau, where tau is the average relaxation time, upon m, where m is the mass of the conductor. Here relaxation time means under the influence of external electric field, what happens? The electrons, they get accelerated, okay? They get accelerated and they move, they drift in a direction opposite to that of the applied electric field. But okay, so under the influence of this external electric field, the electrons, okay, they experience a force and they accelerate, okay, and they accelerate in the direction opposite to that of the direction of this applied electric field, external electric field. But as the electrons accelerates, okay, they suffer collision with the positive ions of the conductor, and hence their increase in velocity, okay, their increase in velocity will be reduced. So the acceleration of the electrons under the influence of this external electric field lasts for a very short time. That is known as your relaxation time. So relaxation time means the short time interval for which the electron accelerates under the influence of this external electric field before it suffers collision with the positive ions of the conductor. That is known as your relaxation time. And the average relaxation time of all the electrons present in the conductor, okay, the relaxation time for all the electrons of the conductor, the average relaxation time will be given by this tau. Suppose tau 1 is the relaxation time for the first electron, tau 2 relaxation time for the second electron, tau n the relaxation time for the nth electron, then the average relaxation time will be given by tau 1 plus tau 2 and so on up to tau n divided by n. So this tau is your average relaxation time. We have derived this relation for drift velocity in part 1 video of this chapter, current electricity. So if you have not seen that video, you have to first see how we get the expression of this drift velocity, and hence we can use it to derive Ohm's law. Alright? So here, your minus E is the charge of an electron. Your E is the external electric field applied. Tau is the average relaxation time. And here your m is the mass of the electron. This relation can also be rewritten as minus E, means charge of the electron. Now the electric field can also be written as V upon L. The potential applied across the conductor of length L. Okay, so electric field can also be given by V upon L. So that means here V is the potential, that is potential difference that is applied across the two ends of the conductor, and L is the length of the conductor. In that case, your relation will become electric field E means V upon L into tau upon m. If we consider only the magnitude, then instead of minus E, we'll be writing only E, and then V tau upon ml. So this was the relation or expression of the drift velocity, okay, of the drift velocity, which we have discussed in the part 1 video of this chapter. Is it okay? Yes. Here is the charge of the electron, only the magnitude. V is the potential that is applied across the two ends of the conductor. Tau is your average relaxation time. M is the mass of the electron, and L is the length of the conductor. See, your concept must be very clear about the drift velocity. Only then we can prove this relation. Okay? Now also we have seen that the relationship between electric current and the drift velocity of electrons is given by N A E V D, where N is the density of the electrons, A is the area of cross-section of the conductor, E is the charge of the electrons, and here your Vd is your drift velocity. In that case, your I will be equal to NAE. Your Vd can be written as EV tau upon ml. So this relation becomes an E times E square A tau upon ml into V. I can write into V. Now if we cross multiply this relation, then we have an E square A tau times V is equal to ml times I. Here ml is not your Mobile Legends. Here m is the mass of the electron, L is the length of the conductor, okay? So this relation can be rewritten as V upon I. V upon I is equal to ml upon ne square A tau. Now, m means mass of the electron. Mass of the electron. And mass of the electron always remains constant. It is always a constant quantity. Okay, mass of an electron. L means length of the conductor. Length of the conductor. See, length of the conductor can be varied. But if the temperature is constant, if the temperature remains constant, then there will be no linear expansion. Hence, if the temperature is constant, then the length of the conductor will also be constant, because only if you increase the temperature, then there will, due to linear expansion, the length of the conductor will also increase. Okay, but length of the conductor will be constant only if temperature is constant. Temperature is constant. Alright? Now N. N means the density of electrons. Density of electrons. Density of electrons means number of electrons per unit volume. See, the density of electrons means number of electrons per unit volume is also constant only if the temperature is constant. Because if you increase the temperature, then the electrons will absorb that energy, that heat energy of the conductor, and they will accelerate and they will move out of the atom. Okay, in that case, the density of the electrons may decrease. But if the temperature is kept constant, then the density of the electrons will always remain constant. So, constant, N is constant only if temperature is constant. Only if the temperature is constant. Next one, E square. E square. E means charge of an electron. Okay, E or E square. E is the charge of an electron. Charge of an electron is always constant. It's always a constant quantity. Okay, it's always constant. A, area of cross section. Area of cross section of the conductor can be varied, but if you keep the temperature constant, then there will be no increase in area. There will be no superficial expansion. If you increase the temperature, there will be superficial expansion in area. But if you keep the temperature constant, then the area will always remain constant. So A, area of conductor will be constant if temperature is constant. If temperature is constant. And then we have average relaxation time. Average relaxation time. The average relaxation time of the electrons will always remain constant. It is always constant. It depends upon the material. Okay, so it is always constant. M is constant, always constant. L is constant if temperature is constant. N, density of the electrons is constant if temperature is constant. Charge of an electron is constant. Area of the conductor is constant if temperature is constant. And tau relaxation time is always constant. That means V upon I is constant. in that, see, this quantity will become constant if temperature is constant. That's why in Ohm's law, we always need to keep the physical conditions constant, that is keeping the temperature constant, so that this whole quantity becomes constant. And if V by I is constant, then we have V is directly proportional to I, which proves Ohm's law. Okay, so in order to understand the relation for the drift velocity and the relation between the electric current and the drift velocity, you must go back to video part 1 of the current electricity, which I have uploaded, okay, few days back. And using those relations, we have proved Ohm's law.